The plan for this lesson is to discuss principal component analysis. We will go over the key idea, how PCA works, and apply it on the Iris dataset. The key idea in PCA is that data vary more strongly in some directions more than others. Because all of these data points cluster or give a specific shape, that suggests that they have a direction from a linear sense. So to get a good approximation, we need to find those directions or this linear model because we're going from higher dimensions to lower representative dimensions. What is a principal component analysis? Let's go over the textbook definition. It's a statistical procedure that uses an orthogonal transformation. But what is the orthogonal transformation? It's a transformation that preserves the vector's original length and angle. In other words, it's a transformation that preserves the direction, and the correlated variables will tell us something about the amount of variance and its significance. So we need to find those correlated variables because they will give us one strong direction. The second strong direction is going to be the opposite direction, or the perpendicular or orthogonal. In summary, data is very high dimensionals with many number of features, and what PCA does, it finds a linear combination of representative features that explains the variation inside the data the most, and then we transform the higher dimensional data to those components. So it's a linear combination of original features that captures the significance, variance, or the direction inside the data. How PCA works in high level without getting into the linear algebra side of it. So in the problem formulation, we have an n-dimensional data set, and our goal is to find those k principal components, hopefully k is less than n, and then transform our original n-dimensional data to those k linear combination dimensions. First, we pre-process the data, we do mean centering, then compute the n principal components as follows. We calculate the covariance matrix, then calculate the eigenvectors and eigenvalues, sort the eigenvectors, and find those k eigenvectors that explains the variance the most. Once we have those k dimensions, we transform the data. In this example, we will apply PCA on the Iris dataset, which consists of 4 features: sepal length, sepal width, petal length, and petal width. In this graph, we plotted the data before finding the principal components, and as you can see, using the sepal length and sepal width, we were able to separate setosa, appearing in red, but the versicolor and virginica data seems to be intermixed. This is the Python script for finding the principal component, and we start with reading the data from the source, then finding the mean center of the data, which means subtracting the mean from the values, because it's going to help with removing the bias and ensure that the variance is computed correctly around 0. Sometimes this step is not explicit. The libraries would do it in the background, but we added it here anyway. Next, we initialize the PCA model, and notice here we specified that k equals 2n, so we're going to have a full transformation. Then we call PCA.fitTransform, which will find the principal components and transform the data to the new principal components. In this graph, we plotted the transformed data using the first two components and contrasted with the original data plotted against the sepal length and the sepal width. So as you can see, the Setosa species become even more separated, and the versicolor and virginica are less intermixed. Now we get to an important question: how to choose the appropriate number of components. So for each principal component, we can compute the explained variance ratio, which is going to tell us how much variance this principal component captures. And we try to find a good place inside this graph to cut the number of principal components. For instance, as you can see here, by reaching the second principal component, we are no longer gaining variance. And the cumulative explained variance plot shows this even better. So by reaching the second principal component, we reached about 98% of the cumulative explained variance. So having two principal components is good enough. And here is another example to reinforce the idea of choosing the appropriate number of principal components. This is the digits dataset, which consists of 8 by 8 pictures of digits, which means there are 64 dimensions. So as you can see here, once we reach the 10th principal component, we gained about 80% of the cumulative variance. And if we stop here, maybe we will still get good results.